I guess I made that, what, Bernie Sanders joke yesterday, so I won't make that joke again today. Having so many people here now. Anyhow, so after this, we will go, for those of you of age, go meet the VR and have a beer with Charlie, unless he's being family as well. But anyhow, it's with great pleasure. We're going to do the double introduction thing, and that's really appropriate because Charlie started out as my advisee, and that he's going to leave one of the very most organized advisees I've ever had. And so it's really nice because you set him in a particular direction and he just goes. But became even more important as I've been gone during the summers for research sometimes, and Charlie has provided, how should we say, the stability in the lab. And we had 5 new people, and they were all panicking. They'd go to Charlie and go, what do I do? And he's like, this, and this. And it was all perfect. And so he's also been a pioneer in terms of working with 2 professors at the same time. So basically trying to please 2 masters.
Mostly.
Right? Mostly him. And so I'm going to leave it now to Stefan to finish off.
This is perfect. This is our stewardship of Charlie's job. On me. So I took Charlie on as a research student after we had Act 2, which some of you are in right now. And you know, I like to think that people that have gone through that class can do anything. I can just give them instructions and they can try stuff. And if it doesn't work, they figure out why it's not working and try other things. And it turns out that assumption is not always just not always, but in this case it was. So Charlie was able to see why things didn't work. I wish I would have had him for longer, a couple more years, or get rid of all this other stuff he does. To have him in the lab for 40 hours a week, that would be nice. But I suppose it's not very nice. So Charlie is going to talk about what he's done today. He's going to talk about a really wide range of what organic synthesis is, how we make stuff, and sort of how we know we've made it, what we do if we don't know if we've made it, or if we know we can't make it. And then he's going to talk about some of the biochemistry too. So it's a wonderful example of a broadly trained liberal arts chemist. I'm really excited. I'm really excited about watching him soar next year as a graduate student studying organic chemistry at the University of Colorado Boulder, which is almost as beautiful as Appleton, Wisconsin. They'll get there. That's what we're trying.
So today I'll be talking about my project-based exercise in medicinal chemistry, synthesis and screening of potential antimalarial compounds. So why study malaria at all? Malaria is a parasitic disease. It's transmitted by parasites in the genus Plasmodium, especially Plasmodium falciparum, which you can see here and here hanging out with some red blood cells. Malaria causes 500,000 deaths every year, and most of them are children in Africa and other tropical regions. So this is actually the #1 most deadly neglected tropical disease, which makes it really important to study. Additionally, the parasite evolves really quickly, and so it can develop drug resistance, so current medicines aren't going to be effective for an extremely long amount of time. So that requires us to constantly think about formulating new medicines that will be effective in the future. So how does drug discovery work? So we start by finding some sort of lead compound, and a lot of them are isolated from nature. People have been using medicines for thousands of years, and scientists are happy to go and use information that other people have already figured out. So we talk to native healers and other sorts of people that do natural remedies and figure out what compounds they're using, and then take them and see how we can make them better. So we test lots of different compounds that we've made on parasites and look for compounds that kill the parasite. And then we look at ways that we can improve those to make a more effective drug. So a specific example I want to share with you is chloroquine, which is an anti-malarial drug that's used right now. It started with quinine, the structure which you can see here, which was isolated from the cinchona tree in Peru, and they use it as an antimalarial there. It's in tonic water, but there are some adverse effects to using quinine. So scientists took this structure and they said, okay, what are the important parts of the structure that we need to preserve? And you can see those there, right? You can see this ring system that's pretty well preserved in both structures. And by 1934, we developed a new drug called chloroquine. Now, it wasn't put into use for many years after that because people were nervous about the chlorine being in there, but it actually is a very effective antimalarial drug that we still use. So a couple of statistics about drug discovery. Today it costs over $1 billion to develop a single drug because there's so much work that goes into it. It's also a really time-intensive process. It can take 12 years or more to get a drug from the first, the kind of the twinkle in the eye to actually being a drug that gets used. The success rate is much, much less than 1 in 1,000. So here's a diagram of the process. So we start, so the work I'm doing is mostly in this area. So we're drug discovery. So we're finding a target, we're looking at lead compounds, and we're trying to optimize them. And we can make 5,000, 10,000, or even more compounds. And then we find maybe 250 that show some effect against, in my example, the malaria parasite. Then that will go on to clinical trials. There are 3 phases of clinical trials, each one with successively larger number of participants. The first step really just determines toxicity and potential adverse effects. The second and third phases are the ones that determine the actual profile of the drug and its effectiveness against some actual illness. Then after that, we maybe have one drug. So so this funnel is not really drawn accurately, right? This should be like huge, and then we get down to one single drug. So it's a really, really time-intensive and resource-intensive process. So for malaria, this isn't really a great model because with its prevalence in third world countries, it's not extremely profitable to sell this drug. So our large pharmaceutical companies are not going to be especially interested in producing this drug because they're going to put in a lot of time and a lot of money and not really be able to get a return on investment. So it falls to people like us. And we've worked on this project through open source malaria. So open source means that no one pays for information. And so it's an open community. It's based in the University of Sydney, Australia. So it's really a worldwide project. We share information on the internet. People contribute from all of their different disciplines. So we're mostly on the synthetic end and a little bit of biochemistry testing, but other people do target identification and come up with compounds that they think we should try to make. And then we send them somewhere else and they're tested against the parasite. So people all around the world are involved in this project and no one is really making money off this. And that's because there's a lot of money to be found in this, but obviously it's a really important venture. So at Lawrence we have this project happening and our objectives are both research-based and educational. So on the education side, we're looking to develop laboratory skills. So we take skills that we've already worked on in class and then we apply them to a project. And we also get to experience interdisciplinary science. So the project you'll hear a little bit about more later takes place in 2 courses, Organic Chemistry 2 and Biochemistry 1. And many students take both courses. They're both required for the chemistry major, the biochemistry major, and I think most pre-medical students end up taking both of those classes as well. So a lot of people get to experience this project on 2 angles, and that's a really neat opportunity to see how the scientific disciplines fit together. On the research side, we get to explore new synthetic methods. So you'll see at the end of my talk, I'll show you a really cool radical reaction that we just tried, but the reason we tried it is because it brought us closer to the compound that we were trying to make. We can understand structure-activity relationships. So that's looking at the actual structure of the compound and then how it relates to the activity of the drug in biological systems. And the ultimate goal is to possibly find new compounds with antimalarial potential. But as I put on here, we can also rule out compounds that don't work. and that's also really important. So how does open source malaria work at Lawrence? So first, the project people from the internet send us a lead compound. We do some small scale synthesis in the research lab, and that's where we test new methods, see like, okay, maybe this will work, we can try that. Then we send it to the students in organic chemistry too. So these are second semester organic chemistry students. We introduce them to the project and give them information and say, okay, try and make some stuff. And they do that. Then we give it to Biochemistry 1. And in that lab, they test for anti-inflammatory effects. And then we can send the compounds on to open source malaria to test for anti-malarial effects. And then if they're successful, which in a couple of cases they have been, there's a possibility for future development. So in organic chemistry 2, students are synthesizing a variation on this core molecule. We'll talk about the shape of the molecules in a little bit. So this builds on the synthetic chemistry skills that they've developed in lab. So by the time this project starts, they've had probably 15 lab sessions in organic chemistry. So that's like 60 hours of lab. So in just this discipline. So theoretically, at that point, you've developed enough skills that you can work somewhat independently and actually do a reaction on your own. So this is a cool opportunity to do that in something that has an application and not just making a product that we throw out at the end of the lab period. Students work up and analyze each intermediate. And so what that means is they're actually purifying the reaction mixture and isolating the final product, and then analyzing it using a variety of spectroscopic techniques to actually determine if they made the molecule they were trying to make. In my case, I did not do that. It did not work. But that's why I got to do research later and do some things that did work. They also write a full lab report, which is a great way to kind of synthesize all the information together and get a coherent view of the project and how their work contributed to it. This is Annabelle in biochemistry. She's representing what happens in the biochemistry lab. Students test the molecules that were made in organic 2 for anti-inflammatory effects. There are a variety of ways we do this. The first one is cytotoxicity with the crystal violet assay. And so there we're just testing to see whether or not the drug kills the human cell that we're applying it to. And I'll talk more about that one later. We're also testing for nitric oxide production with the grease assay. Nitric oxide is a marker of inflammation because it affects your blood flow. So that's a good way to test if the cell is producing nitric oxide, then that gives us a hint as to the inflammatory response. We can also test for NF-kappa B inhibition with a time course and a Western blot. And NF-kappa B is another marker of inflammation. So these are relatively simple tests that we can do within the lab period that will give us some hints as to whether the drug has an anti-inflammatory effect. But I thought we were making anti-malarial drugs. Why are we testing for anti-inflammatory effects? Well, the first consideration is it's just simpler and safer for undergraduates to work with. We've got a lab section, and we can use HeLa cells. If you've read the book, The Immortal Life of Henrietta Lacks, you know about those. They're a fairly easy cell culture to work with, so it's good for students that don't have a lot of experience working with them. And the tests are fairly straightforward as well. Also, we do care about anti-inflammatory effects. Those are desirable in a malaria drug because if you are infected with malaria, you will have inflammation. So it's also helpful to have some anti-inflammatory effects in the drug. An example of another dual-purpose drug is azithromycin, which is an antibacterial that you may have taken, but it also has anti-inflammatory effects. So those are really desirable in our malaria drugs as well. Okay, so now we get to the crux of the project, which is the synthesis that I did. But first, what is synthetic chemistry? Well, it's kind of like baking. So we start with a recipe. We have a list of ingredients, and then we have directions for how to combine them and mix them together and what to do. And then if you follow the instructions, you end up with a baked good, like these cupcakes. In synthetic chemistry, we use this thing called a prep, which I cropped the photo so it looks just like a recipe card. So it gives us a list of ingredients, and So here it says H2O2, 30%. This is the quantity, 7.5 millimoles. And then it says how to combine them. Added dropwise over 2 minutes at room temperature to a stirred solution of 2.5 millimoles of heteroaromatic base, etc. And then if we follow those directions, we'll get a product, a chemical compound. So to explain it in kind of the philosophical terms of how we do this, we start in our minds with a target compound or class, and then we are transforming a starting material to make the final product. So in this example, this is towards the thing that we're trying to make. But this would be our starting material, an acyl chloride, and we're going to react it with anisole, triethylamine, dichloromethane for 30 minutes, and then we'll make this compound. How do we find these? Well, we can get protocols from other papers. So there are other synthetic chemists around the world that are also doing synthetic chemistry, and then they publish what they did, and then we can just read it and be like, oh, I also need to do that, and then we just copy what they did. Sometimes, though, we're doing things that no one else has done exactly, and so we adapt an existing reaction. So you might take a reaction that looks like this, but maybe they use a different group over here, and we might be like, well, the chemistry is pretty similar, so this will probably work. And then we try it, and then hopefully it works. And then an important thing we have to do is to analyze at each step. So I think this is like an oil, so that's kind of an outlier. But most of the compounds of this size that I work with are crystalline solids that are like white or yellow or like maybe brown. So you can't just tell, unlike the cupcakes, you can look at it and see, okay, yes, I made a cupcake, and you can eat it and be like, wait, it's good. With a chemical compound, you can't just look at it and see if it's the thing that you were trying to make. So we have to use some pretty sophisticated analytical techniques.
Don't eat, please don't eat.
Yeah. So we can't eat them, and we can't just like tell by looking at them. So we have to use some other techniques to really determine if we've made the compound that we're trying to make. Okay, so what we do is create a synthesis plan. So that might look like that. We execute it, so we actually do the thing, and then we ask ourselves, did it work? So this is the synthetic chemist toolbox. So this is something that we use a lot. If you've had organic, it'll look familiar. This is our reflux apparatus. So right here we've got a round bottom flask, and that's where we actually put the things that we're reacting. It's our pot. So we have all of our reactants, all dissolved in some sort of solvent. Usually they're volatile organic solvents. We don't do them in water because of solubility issues. So things like ethanol, dichloromethane, those are our solvents. And then we heat them to boiling. But like, you know, if you're making like a soup, a lot of the water boils off and then it gets thicker. That would happen really quickly with volatile organic solvents because they have a low boiling point. And so to reserve the solvent, which is both a practical concern and also an environmental concern, we use a West condenser, and it's actually pumping cold water through the outside, and then on the inside, any evaporated solvent will condense back down into the pot. So it's a really useful tool for doing synthesis. And then this is me working in a hood. The fume hood is used because, again, of all those volatile solvents, I don't really want to breathe them in. So yeah, this picture is a weird shape. So there's a glass door that I actually slide down in between my face and all the things happening. So that protects me from fumes, and then also if there were to be some sort of dangerous explosion, there'd be less probability of like glass flying at me. So that's just one of our safety things. Okay. So now we can start to look at the actual chemistry that I did. So this is the class of compounds that I've been working with my whole time here. These are the 1,2,4 Triazolopyrazine pyrazines. So that is a really long single word, but it's actually made up of a lot of little pieces that describe the shape of this general molecule. So we'll start with the 1,2,4 triazole. So that describes that ring. And then the pyrazine describes this ring. And then the 4,3A describes how they're connected. So that's just a general way that we can describe the molecule we're working with. So this fused ring system has been determined to work really well might work really well as an anti-malarial drug. And And so these are the things that we're trying to functionalize. And the R group means any sort of thing that we're attaching. So these two carbons are actually the places that we're trying to attach other molecules in an attempt to make something that will be an effective drug. So the first project I worked on was the optimization of the hydrazone formation. And that project came out of the year that I took Organic 2. We did not have a super successful time, and so we were looking at ways that we could accomplish the same transformation, but we needed to do it a different way because the order we did the steps didn't work out. So the first thing I did, you saw this before, I use it as an example, started with this acyl chloride. This is not a trivial starting material. It was a 5-step synthesis to get to here, but it's all minute changes, so I didn't put it in the talk. React with anisole. This is a catalytic nucleophile. Triethylamine and then dichloromethyl is our solvent, and we're able to make this amide in pretty high yield. Next, we're going to reflux with hydrazine, which is diluted rocket fuel, in ethanol, and we're going to make the hydrazonyl pyrazine. So, okay, so I'm saying we made this, but how do we know we did that? So what I do is take a compound when I make it, dissolve it in solvent, and put it in the NMR in the basement. And I get a group of lines like this. So what do those mean? Well, nuclear magnetic resonance spectroscopy is probably the most useful technique for synthetic chemists because it measures the effective magnetic field experienced by the molecule. These are strongly affected by neighboring nuclei, so we can get really detailed information about the environment experienced by each molecule, each atom in the molecule. We can study different atoms. The most common one is hydrogen 1, a proton, because they're really, really popular. They occur, 99% of hydrogen atoms that occur are 1H. So that makes it really easy to study. We can also study carbon-13. That doesn't occur naturally as often, so there are some issues with that. But we really want to be able to study carbon as well because as organic chemists, most of our molecules contain mostly carbon and hydrogen. And there are many, many more. Anything with an odd isotopic mass can be studied if you have the right equipment. Okay, so here's a picture of our NMR. Right there is actually where the magnet is and where the sample goes in. Should have taken a picture from the other side. This is the computer that controls everything. And this is our auto sampler, which is very convenient because we can load 96 samples and then a robot sends the spinner into the magnet. And as long as your spinner has a tube of sample in it, it'll be able to pull it out. Okay. So this gives us the number of hydrogen atoms in the molecule, and it also gives us information about the environment, about these protons. Now I'm generalizing down to just a proton NMR, but any atom that is able to be studied will get information about the number and also, most importantly, about the environment. So let's go back to the spectrum I got. You can see this is on a scale of parts per million, and what that is showing is the chemical shift, which is actually the shift in frequency. I just went to a lecture about this 40 minutes ago. Thanks, Allison. The shift in frequency caused by the effective magnetic field experienced by the nuclei. So we're looking at hydrogen nuclei, and I have color-coded them to match the arrows that are now going to appear. So highly deshielded means that they're near an electronegative atom, most likely. And so nitrogen is very electronegative, and so the protons attached to the nitrogens are going to be shifted upfield. So we identify these two as being these peaks representing those hydrogen atoms. And you can also see that these protons are fairly close to this one nitrogen on the pyrazine, so that's them. And then these are on an aromatic ring, so they're actually still pretty deshielded. You can see the scale starts at like 6, so I've actually cut off the first 6 ppm. So all of this stuff is pretty highly de-shielded. So the greens are going to show up there. Now if you look closely, you can see that these peaks are actually bigger than these. And that's because we can use integration, the area under the curve, to find the number of atoms represented. So each of these have an integration of 1, and then these two peaks have an integration of 2, because they're both representing 2 protons. And the reason those are equivalent is because this bond can rotate. So these two are basically indistinguishable from each other. You can also kind of see that there are actually 2 peaks for each of these. And that's because of splitting, because they're so close to another hydrogen nucleus. That's going to affect the way that the data shows up. Okay, so with all of that, oh, and actually here's a little bit of residual starting material, just for fun. So I'm pretty sure I made that, so that's great. So will it work? So I made a molecule, and that's pretty cool in itself, and it feels good to know that you made something. And I think it was like July of summer research before I made that, because I tried a lot of things that didn't work first. But now I want to know if it's effective in a biological system. So the first test is for effects on cell viability. Okay, so imagine that you have a headache, or maybe this is too real, and you do. Okay, and you'll take a Tylenol, so acetaminophen, or maybe an ibuprofen, to try to get rid of the headache. But let's say that the drug kills you. Is that an effective drug?
No.
No. Okay. That's well, right. So it's like it does get rid of the headache, but that's not really what we want to have happen. So the first thing we want to test is whether or not it's going to kill the host cell, so the cells of the person who's taking the drug. So that's a cytotoxicity test, cell toxicity. And this is actually fairly straightforward. So we take HeLa cells that I was talking about in a plate, we can apply the drug, wait 24 hours, and then use this crystal violet assay to determine the cell viability in relation to some control. So crystal violet is a stain that stains cells that are going to be left on the bottom of the plate. And HeLa cells actually are adherent cells. So if they're growing in a plastic plate, the cells that are alive will stick to the bottom of the dish, and dead ones will float. So all we have to do is remove the media that contains the dead cells, and then we can put crystal violet on the bottom, and the color will change depending. And this looks bad because the cells survived, so it's not very interesting because they're all the same color. So that tells us how well the cells survived with the drug treatment compared to a control where we just had the cells growing in a plate without any drug treatment. So here's my data from this compound. So we set the control to be 100% cell viability. And then we found that with dimethyl sulfoxide, which is just the solvent that we use to dissolve the drug in so it could enter the cells, also 100%. And then close to 100% cell viability with various concentrations of drug. So we determined that it was not toxic to HeLa cells. So then we did another synthesis, and now we're actually, this is the one to actually make the hydrazone. React with piperonal, sorry, these are two separate things. Piperonal is an aldehyde, and that's actually going to get displaced by the nitrogen, and then we're going to make this functional group called the hydrazone. Now, if you look, this looks pretty close to the triazole part of the triazolopyrazine that I was trying to make. So we're actually one step away from completing oxidative cyclization to actually make the second part of the fused ring system, and we would have had the complete molecule. Unfortunately, word came down that this mid-functional group is something that we don't want to try to make anymore because we found out that it can cause heart problems in this drug. So we moved on to something else. And this project was the functionalization of the triazolopyrazine core with boronic acids. So we said, what if we start with the core molecule, instead of forming this ring at the end, why don't we do that first and then add other stuff on? So that's what we're looking at now. So to do that, we needed radical chemistry, which is not just for the 1960s. So the most common radical reaction, is kind of an umbrella term, is the Minnesy reaction. And it's a radical-mediated aerylation, which just means that we're adding some sort of aromatic system using a radical intermediate. So here's the thing that we're trying to add it to, and here's the radical that we're trying to add. So there are 4 steps in a radical immunicity type reaction. First is to generate the radicals. So we use boronic acids, a paper by Phil Barron, and we're just going to split this bond in half. So now we've made 2 radicals, and I should mention that radicals are single electron species. And so they each have like 1 extra electron, and that makes them very, very reactive. Next we need to protonate our heterocycle. Thankfully, nitrogen's heterocycle, is a ring system, that's a cycle, that has a heteroatom, a nitrogen or an oxygen, instead of just being a bunch of carbon and hydrogens. So this is, yeah, definitely a heterocycle because it has 4 nitrogens. And the legend goes that every nitrogen atom in your molecule adds a year onto your PhD. So they can be somewhat difficult to work with. So we're protonating with some acid. Next is the crux of the reaction, the substitution to form the intermediate. And then finally, re-aromatization, oxidation. This is not quite as stable as that. So specifically the reaction I did was to react the chlorotriazolopyrazine with phenylboronic acid, and that generates a phenyl radical that's just going to attach right onto that carbon. Unfortunately, I did not have very much starting material to work with because this is very difficult to make as well. So we did this on a really, really small scale, 2 milligrams, which gave us some challenges for trying to determine whether or not the reaction was successful. So we turned to gas chromatography and mass spectrometry, or GCMS. 1 machine, 2 different things. So here's a picture of RGC. So chromatography is a technique where you separate compounds based on polarity. This is not the only chromatography that we do. We have column chromatography, and we have thin layer chromatography, and we have liquid chromatography. But this is gas-phase chromatography. Mass spectrometry then is how we find the mass of the compound. So here's a diagram of the GC. So we'll put our sample in here, and then there will be gas coming in here, and we'll inject it through a temperature-regulated oven, and we'll have a packed column, which it will go through. It's a very, very long column that's all spiraled up together, and then the compounds will come out into the mass spectrometer detector. So compounds are going to separate out based on their polarity, and the value we assign to that is the retention time, which is the time in minutes that it takes for a compound to get through the column. So a longer time means a more polar compound, and I'll show you that on the next slide. Polarity is just unequal sharing of electrons within a bond. So here you can see we've just injected our sample, and there's actually 3 different types of shapes in there. Now they're starting to separate out. And so the column is actually very, very polar. And so kind of going along with the like dissolves like thing that actually relates to polarity, polar compounds are going to stick to the column a little bit easier. So we can say that this blue shape molecule is going to stick to the column more than the yellow one. And then by the time we get to the end, that's why we need a really long column. They've actually separated out into 3 distinct groups based on their polarity. Then they go into the mass spectrometer. There's 4 steps. First is ionization, and that just removes electrons to make ions, which we'll need in order to measure the mass charge ratio later. Next, we'll accelerate them to an identical kinetic energy. Then they'll be deflected, and that's done with an electromagnet. And this is where the ions become really important, because the deflection will actually vary depending on the mass charge ratio. So then we can detect when they come into the detector, and then that actually gives us data that we can look at, analyze, and determine whether or not what sort of molecules we have. Okay, so here's some data. This is the GC trace. I've cropped it to start at about 9.7 minutes. Nothing happened before then. So we identified some of the peaks. That one is biphenyl, a byproduct. Phenylperoxide, a byproduct. This little peak we figured out was our starting material. And then this significantly larger peak, thankfully, was our desired product with that added phenyl group. Okay, so how do we know that those are the peaks? We can make some sense of it with polarity, right? Like this doesn't, this has like these boron-oxygen bonds, and this is just carbon-nitrogen. But this is where the MS becomes really important. So we can actually look at the mass spectrum peak, and it's actually a series of peaks. We can get a lot of information just from the first one. So this is our product, and you can see the mass charge ratio values that were calculated for us based on the isotopes. So nitrogen has a couple isotopes, important isotopes, so does carbon and so does chlorine. And so there are several possible mass charge ratios, and they'll occur in these proportions. And we can actually match that up with this peak. So the largest one is the 230.04, and then the second largest one is about a third of the way up, and that's 232, and the other little ones. So we can be fairly confident that this is at least the mass of the compound that we were trying to make. We did also do crude NMR. So here we're looking at an NMR of the starting material, and there are just 3 hydrogens, and you can see they're all highly de-shielded because of the number of nitrogens in this molecule. And then here is our crude product. So this is the thing we were trying to make, but there are some other things in it as well. So we can see that some of the peaks actually are staying in the same place. So the scale shifts a little bit, but we've got a hydrogen peak around 8 and then another one around 9.1. So we can gather that those are probably the 2 hydrogen peaks that were preserved between the 2 structures. Then we find this nice doublet at 8.2, and that's going to represent the orthophenyl hydrogens. So that one and that one. Ortho just refers to their position on that aromatic ring, and we know that it's a doublet because they're each next to one other hydrogen. And then we can assume that the rest of them are trapped somewhere in this giant mess, which is because we use a lot of phenyl groups. So lots of things like this are going to form all sorts of different byproducts, so they're just that big jumble there. Interestingly, we see a loss of this peak at about 9.35. You can see there's a tiny one left. That's probably the residual starting material. But definitely it's not in the same ratio as it was before, which was 1 to 1. And because we know that the most de-shielded hydrogen is the one between those 2 nitrogens, we can gather that the phenyl group has displaced that hydrogen with that carbon. So we're fairly confident that we are able to make that molecule. We also tested another thing on HeLa cells, and again we saw low toxicity. So in summary, first thing I did was functionalize pyrazine with hydrazone and an amide. Then I used radicals to functionalize the triazolopyrazine core. I used several spectroscopic methods, NMR and GCMS, to analyze the compounds I made. And I determined that many of the intermediates were non-toxic to HeLa cells. So where do we go from here? One possible avenue is sulfur chemistry, having one of those side functional groups involve sulfur. That's what this is a picture of. And then photochemistry. This is a light bulb. And so we can actually use visible light to catalyze reactions and to generate those radicals. So this is actually a photo of a student's reaction in organic chemistry 2 on Tuesday. I took that. And so we're using light to generate radicals and do some more of that chemistry. So I'd like to thank these papers. I want to thank all the chemistry faculty, especially Dave and Stefan, who were instrumental in getting me started in research and helping me through all of the various challenges and twists and turns. And I want to thank my research friends, Haley, Brianna, Michael, Annabelle, Lindsay, Hikari, Lauren, Jay, Grant, Emily, Veronica, Taylor, Brandon, Tyler, and Kasonia. We've all lived in the research office in the last 2.5 years, and that's been a catalyst for really good conversations and commiseration about various projects and things. And so I'm very grateful for the support of all of them and for all of you for coming today. Thank you. cells in the plate because we're just using like a 1,000 microliter pipette to put the cells in the plates. So there can be some slight variability there. So maybe this one, the control just didn't have as many cells to start with. It's like a big possibility. Right?
In your NMR, for your first compound that you were making, maybe you cut it out, but was there not an NH2 peak?
Oh, yeah, I cut it out and I forgot to tell you. Yeah, the NH2 peak is at like 4.5, I think.
Okay, cool.
Yeah, and then the...
yeah, can I see the radical mechanism? I'm just curious about it.
Is that where it started?
Yeah. Just one slide back a bit. Okay. Thanks. Really fast.
No, it's really cool.
Yeah, I like it.
Other questions?
So when you were talking about going through different directions as the next step, why choose sulfur for a possible way?
I don't have a definitive answer. The people in Australia have that, but I think it has to do with the biological target. And they can do computer simulations that would suggest that having a sulfur in there would increase the biological activity. Yeah.
So when medicinal chemists are changing molecules, we want to make little changes. And so if an amide won't work, a short jump is to just change the carbon in an amide for a sulfur, like a sulfon amide, or a sulfonyl group, or a sulfone. So it's called an isosphere, something that's going to act kind of like it and look sort of like it, that'll be just different enough to do what's tested.
So you start off from the big picture, like drug development for this open source malaria project. How many different types of compounds do they send you, and are they very similar, or do you start with a very broad range of compounds and then you select one that has specific characteristics? So can you explain a little bit more about that procedure for selecting where to begin?
Yeah, so at least on my end, I get my targets from Seven, get them from them, and I think what happens is they send kind of a general thing, so like, let's try, let's see. No, not that one. So, like here, they might say, okay, let's try having some arrow group there. And then Seven says, oh, let's try with phenylbronic acid because that's the cheapest one. And then that's where we start. So does that help?
Yeah.
Yeah, so they kind of provide like a general target, and then we kind of choose specific ones based on other factors, and then hopefully would be able to try it with lots of other boronic acids that exist that we can make lots of variations.
I have another question. So in one of the syntheses you said, this is actually not, I mean, it's your starting material, yes, but so there was like a whole bunch of steps up to that point. I'm curious, in all of your, I mean, I'm sure you've done hundreds of syntheses, steps, was there any one in particular that you were surprised didn't work, or just kind of came out of nowhere, you're like, I have no idea what happened?
Yeah, it was actually, I had a very interesting time. I don't have a picture of it, I don't know why I'm looking for it. It was,
That was the fastest molecule I've ever seen.
That's really good.
it was doing the chlorination reaction, and the reagent we used was sulfonyl chloride, which is really gross. Because if it reacts with water, you get sulfur dioxide and hydrochloric acid gas. So neither of those things are good. So it was kind of like on the edge of my seat thing. But actually, when I purified it, the first time I tried to purify it, it was an oil. But then it started to crystallize, and there were these little needles that grew in it over time. And I just let it sit for a while, and then was able to grow some crystals of pure compound. So it was cool to watch them kind of grow. And it was also fun the time that we made it, and then the distillation didn't go quite as far.
Also, when you set that reaction up, it's catalyzed by a few drops of this catalyst. And there's always a time lag, and I always forget that there's a time lag. And so you add a drop, and you're like, a few more drops, nothing. And then that fourth drop just bubbles everywhere and foams over and goes crazy. And every time I do it, I'm like, that's flame.
Katie?
I'm wondering, you mentioned earlier how natural products could sometimes be used in the process of working on finding these remedies. Did you use any in yours? And if not, where along the process of working with these chemicals would that be added?
You know, I'm not entirely sure where they found the triazolopyrazine. That's where the natural products would come in, is that someone would find, so like with quinine, quinine was a naturally occurring compound, and then they took that and made improvements. So with the triazolopyrazine, I don't.
Where does the whole project start?
Yeah, so this came from, thank you, that came from the malaria box, which is in Europe, and they've got this whole box of compounds that you can test. And so that's kind of where this one originated from, and not so much from like an agent remedy.
Even before that, it was like a million compounds tested.
Yeah, oh yeah, so they have like a giant list and then test them. So natural compounds were on that list, the giant list. I don't think that the triazolopyrazine was ever from a natural compound.
No.
Just guessing based on that it's difficult to make. I have not sent anything in personally, because they haven't been like 100% to the thing that they want. Because you have to, in order to like have like the complete thing, it has to have the fuse ring and then be functionalized on both sides. So, yeah.
It's kind of amazing that he's able to get so good data at the end from 2 milligrams and stuff. 2 milligrams, 2 milligrams. Great. Let's congratulate him on his work.